Lesson 5.1 and 5.2 introduces linear systems of linear equations. And in this lesson, we're going to start solving them using graphing and substitution. So what exactly is a system of linear equations? Really, it's just two or more equations using the same variables. Two or more equations in the same variables. All right, now you might just be thinking, well, every darn graph we use has an x and a y. A little more specific than that. The variables should represent the same information. All right, so an example of this would be two phone plans that have a different starting price and a different monthly rate. Well, which one's better? They're going to be better at different points in time, and there's going to be a point where they cross over and they're the same. That's the point of solving linear systems, is basically to compare two of the same idea and figure out which one's better at certain points in time. So when we say solution to a system of linear equations, it's an ordered pair, so a point on the graph, an ordered pair, an xy value, that is a solution for both equations. I'm going to say each equation, because it is technically possible to have three graphs on a system. It's just then you might not have a single crossover point for all three unless you plan ahead. So this is essentially what systems of linear equations are, is a way to organize and look at multiple equations that are talking about the same thing. Prices of hotels, prices of phone plans, just that sort of stuff. Something that has a rate tied to it, how expensive it is to live in different apartments. Here's our first type of question, just to reinforce that idea of what a solution is. So for this point to be a solution, it has to work for both of these equations. So if I plug in my x and my y, 2 plus 5, I like to put parentheses around things I plug in. 2 plus 5 equals 7. That's true. Give that a little happy face or something. And then 2x minus 3y. 2 times 2 minus 3 times 5. Does that equal negative 11? 2 times 2 is 4. 3 times 5 is 15. Yes, 4 minus 15 is negative 11. So that's also true. And if they're both true, the answer is yes. It is a solution. All right, let's do one more. Does negative 2 comma 0 work for both of these? Let's plug our x and our y in. Y is 0. Negative 2 times negative 2 minus 4. Negative 2 times negative 2 is positive 4. Is 4 minus 4 0? Yes, so that one's true. Now over here, 0 for y, negative 2 for x. Negative 2 plus 4 is 2. That is not true. So this is not a solution. All right? So what we mean by solution is if I were to graph these two lines, if my answer is yes, then that point is where the lines cross each other. If my answer is no, then it's some other point. So in this case, it would be on the left line if I were to graph it, but it would not be on the right line, so it would not be their crossing point. Next thing to look at is actually solving by graphing. And this actually opens up a way for you to check your work this whole unit, is if you go to Desmos and type in two equations and hover over where they cross, it'll tell you what point they're crossing at. So if you get answers on assignments or you want to look over a review, and you'll be able to find your answer just by going to Desmos and typing in two xy equations and hovering over where they cross. Obviously, you can't use that for the test. You have to do the thinking yourself, but it's a way to check your work. So first equation's got a y-intercept of 5, and at a slope of -2, so down 2, right 1, down 2, right 1. And we want to find where these cross, so I'm going to get as many points on the graph as possible. Because if they cross right at a nice even point, that's ideal for us. All right. Second graph, let's get a y-intercept of -1 and a slope of +4, so up 4. Yep, there it is. That's where they cross each other. Let me actually get this line drawn. So these are our two equations, and in a word problem, these would be talking about the same thing. All right, now it might be like altitude or, again, cost of different apartments or something like that. We don't know because we don't have a word problem in front of us, but that's what something like this could be talking about. And this is the crossover point. That's at the point 1, 3. So the solution is 1, 3. Right? This is easy, but it's not always practical. What if my answer is a decimal or a fraction? All right, it's not always practical because we have to read our answer from a graph, and if our answer is not at a perfect spot on the graph, well, then we run into some guessing issues. The second method for solving substitution is always practical. All right, this is my favorite way. There's one more method we're going to learn, but this is my favorite method. The next method is going to be our next class period, so that won't be on this notes. But if you take a look at the notes itself, you're going to see a little step-by-step. Solve one of the equations for one of the variables. What's nice is this one already has that for us. Y is by itself. That's important. And then we substitute the expression from step 1 into the other equation. Let's see what happens when we do that. So, I want you to get comfortable using your parentheses. Y equals -2x minus 9. So that is going to replace this y. Because these equations are meant to represent the same information. If I know y equals something, I can replace y with that something whenever I want. So let's see what it looks like after this step. 6x minus 5. Then instead of y, now I have -2x minus 9. This is the part of it that makes it the substitution method. Equals -19. All right, so this equation is the same besides what I plugged in for y. What's valuable to us here is y is no longer in the equation. Since now it's just x, we can actually solve this. We can solve it for x. So my first algebra step is distributing. -5 times -2 is +10, 10x. -5 times -9 is +45 plus 45 equals -19. 6x plus 10x are like terms, so I'll get 16x there. Plus 45 equals -19. I'm going to subtract 45 on each side. 16x equals -64. Divide by 16. I know I'm starting to get into the glare area now. It's my last step. X equals -64 divided by 16 is -4. Okay, now I'm not done. That's just one of my answers. Remember, a solution is an ordered pair. So what I do is I take that -4 and I plug it back into one of my original equations. So now we're going to go from this answer to a new part of our problem. And I get these are going to look big, but I always say this, it's the same thing every time. So once you get practiced with it, it won't feel like so much. So I'm going to replace x with -4. And now I can figure out what y is. -2 times -4 is +8. 8 minus 9 is -1. I have an x and a y value. should write my answers in ordered pair, and this is my final solution. That is the point that these two should cross at. That's the point these two should cross at. It's a lot of steps, but we're going to spend a ton of time practicing this in class. This next example is a little bit different than the first one because I don't have any variables alone. Remember that step one requires that an equation is solved for one of the variables. So what I'm going to do is I'm going to take this first equation up here and I'm going to modify it. I'm going to add x to both sides. And now y is going to be by itself. All right. Now we go back to what we did for the last problem. Y equals this. So I'm going to take this and plug it in for y in the other equation. So I have 3x plus 3 plus x in parentheses equals -1. Now we can solve for x. Y is no longer in the problem for this step. There's nothing to distribute here, so I'm just going to get rid of the parentheses. 3x and x make 4x. -1 hasn't changed yet. Now we'll subtract 3 on both sides. 4x equals -4. Last step, divide by 4. And x equals -1. Remember, that's not our answer yet. We still have to plug that back into the original equation. Y equals 3 plus -1. What's nice is you can plug this x into any of the equations we had. This one just looks easiest to me. 3 plus -1, that's easy. 3 minus 1 is 2. And I have an x and a y value. I should write an ordered pair. That's my final answer. -1 comma 2. That would be the point on a graph where they crossed. Again, we can visualize that by checking on Desmos, which we'll do together a lot in class. Here's an example of a word problem that can be solved using a system of equation and substitution. So a drama club earns $1,040, and that's after 64 adult tickets and 132 student tickets were sold. All right, that is already an equation. 64 adult tickets times the cost of an adult ticket, which we don't currently know, plus 132 student tickets times the cost of a student ticket, which we don't currently know, so we need a variable, should add up to $1,040. All right, adult tickets cost twice as much as student tickets. An adult ticket equals twice the cost of a student ticket. All right, so we have two unique pieces of information. The first equation is talking about the money, talks about total money. The second equation is a separate relationship between the elements, between ticket prices. All right, so these are our two unique pieces of information that made two equations. Now, this is like a number puzzle thing you might see on, someone posting it on Facebook or something like that, like, oh, only 2% of the population can see it. It's not that hard. You're learning it as an Algebra 1 student in high school. We're going to take what a equals, since a is already alone, and plug it in to the a in the other equation. 64 times 2s plus 132s equals 1,040. 64 times 2 is 128. Combine like terms here. That's 260 student tickets. Adds up to $1,040. Divide by that 260. And we get $4 per student ticket. So student tickets are $4. And we can read in the word problem, adult tickets cost twice as much, and just say twice 4 is 8. Or we can take that S and plug it back into an equation. 2 times 4 is 8. Whether we say it in English or we actually use the equation, we should be able to get adult tickets cost $8 out of that. Right? So that's an example of a word problem where we could use solving systems. And cover up that glare quick so you can see all my work. I just got to get something to cover this up permanently. A little shade for it. All right, it's the end of the 5152 notes.